In addition to number of the moles and molecules of the reactant and product that are present in any chemical equation, sometimes you can also have the enthalpy of the chemical equation shown on the right side. So this is the heat of the reaction, how much heat is released in this case because of the sign, or maybe absorbed in a different reaction based on the number of the moles that we have. And so using this information, we should be able to determine how much heat will be released or absorbed depending on how much of product or reactant we have. For example, how much heat will be released if we have 44.8 grams of sulfur dioxide based on this chemical equation. In order to solve this problem, what we need to do is we need to first go back and understand again that these numbers here are very important. As for any other stoichiometry calculations, I would say that 2 moles of sulfur dioxide is reacting with 1 mole of oxygen, producing 2 moles of sulfur trioxide. So here what we need to also understand that all of these moles are directly correlated to the enthalpy of the reaction. And if we change these numbers, which are number of the moles, and represent the chemical equation slightly differently, for example, if you represent it this way, what we can say is that for every 1 mole of sulfur dioxide and half a mole of oxygen, we're going to have a different delta H. It's the same reaction, but depending how many moles of reactants and product we have, this number is also going to change. So 1 mole, half mole, 1 mole. What happens is that everything, the moles have been divided by 2. Everything is decreased 2 times. So as we change the number of the moles, we decrease them 2 times. We also have to change the enthalpy 2 times. So if we have only 1 mole of sulfur dioxide producing 1 mole of sulfur trioxide, we're going to write down that the enthalpy of this reaction is equal to the half of this number, which in this case will be 99 kilojoules. And same if the equation is represented this way, so it's the same equation, but what happened is that now we changed the coefficient, so we went from 2 to 3, right now we have 3 moles, 1.5 moles and 3 moles. It's a balanced chemical equation. It's not wrong to represent it this way, but it's just more practical to use simple numbers. But just in any case, even if we have these type of numbers, we need to pay attention to how the moles have changed compared to the original equation. 2 and 3, we have 1 and 1.5, 2 and 3, so everything this time have been multiplied by 1.5. So if we increase everything by 1.5, all the moles are larger, then the enthalpy is also going to be multiplied by 1.5. And at this time we'll have that the delta H of this reaction is equal to 297 kilojoules. So this is the most important piece of information for these types of problems. We need to remember that number of the moles and enthalpy are directly correlated. As the number is shown, it represents exactly for these numbers of the moles, and if we change the numbers of the moles, we also need to change the enthalpy of the reaction. So now let's think about how we can solve this problem. We have 44.8 grams of sulfur dioxide. What we have noticed is that every time we change the moles, we change this number, the enthalpy, which means that it's correlated to number of the moles. So the first step here is we need to find number of the moles of the sulfur dioxide. So we have this formula, mass over molar mass, and if we do it, we'll have that this is equal to 44.8 grams over 64.0 grams per mole, and this is equal to 0.07 moles of SO2. Now let's look at these numbers. These are the numbers that we have. Initially, the enthalpy is given for 2 moles. Here we had it given for 1 mole. Here we had it given for 3 moles, and every time we changed it. So what you want to think about is, okay, so what if instead of all of these nice numbers, I have 0.07? This is essentially what happens. So in order to solve it, we're going to write down that based on the chemical equation, every 2 moles of SO2, because we have 2 here again, produces 198 kilojoules of energy. And now we have 0.7 from here. It's given here. We have 0.7 moles. So if we write down 0.07 moles of SO2, we can write down that this will give us X kilojoules. We don't know. So if we solve for the X, we'll get 69.3 kilojoules of energy. And this is the final answer. However, there is also the second way how to do it. You could also use the dimensional analysis type calculations, and you can write down that the enthalpy of the reaction is equal to, first we're finding the moles, 44.8 grams over 64 grams per mole. So it's with three significant figures. Step 1, we found the moles. Step 2, we're finding the heat based on the mole ratio of the reaction. So we have 2 moles based on the chemical equation. So we're going to write down that every 2 moles of the, we cancel the grams, so the mole is on top now. We're going to write here 2 moles of SO2 producing 198 kilojoules of energy. 198 kilojoules. And if you cancel the moles, we'll have that this is equal to 69.3 kilojoules. They're both similar procedures, calculating exactly the same thing, however just slightly different approaches, and you can use any of these two.